Okay. So thank you very much. I will start now. Today I'm going to introduce to you this topic for network optimization problems. In particular, how we are going to solve it, let's say using distributed algorithms. This is the outline. I will first give you a short introduction of that kind of resource and interference management problem, and a few reference. So if you are interested, you can trace, and we all can discuss in the future. This talk will be in this for the maximization problem, or you can say minimization problem of the network utility, and in terms of resource allocation. So I will use particularly power allocation or user base station association as example. But you can imagine that you can consider coding, pre-coding, beamforming, or other, okay, or not necessarily wireless. In this, it can work for fiber networks as well. I'm going to focus on this particular category called potential gap, and in this, in particular, in some literature, it is in terms of spatial adaptive play, SAP. So you see, I mentioned SAP many times. Hopefully, this kind of algorithm will allow you to have a scalable and a very flexible one, which means you don't have to synchronize, the operations, which means you ask first user to adapt or to update, and then second or third. I will show you what does it mean by asynchronous later on. And there's a connection of this type of algorithm to another literature in statistical mechanics that people usually say this is a meta-heuristic, or in particular, one of the two is a Gibbs sampling, or in this you can consider as a other category relate. And I will say a few about the simulation result. So this is a general background of the interference management problem. As you know that we have cellular networks. We have a cell such as a macro cell, micro cell, pico cell, and small cell, etc. So definitely they will interfere one another, like the figure on the right bottom. They generate signal like a broadcast channel. So the signal from one base station will interfere, impact a user which is associated with another base station. As you can see, for example, this user, which is going to receive the signal from the base station 1, okay, on the left-hand side, you will receive the signal that you prefer. By the other hand, you receive the interference due to the signal from another base station to another user. So this is the notion that signal and interference, all of them will mix up. What you can do is that you can control the power, which means you say, okay, I don't want to use a large power for user 1, and because it will interfere another user, I will try to reduce, make it smaller, such that the impact or the interference to another will be smaller. Of course, when you do so, your signal to your own user will be small too. So you have to be careful how to trade off the two, make a balance. Of course, you can also consider to use different subcarriers for each user, especially in frequency division multiplexing scheme. You can say I use user 1 or user 2 with base station 1, base station 2 with a different carrier 1 and 2. There's also a choice that the user here, for example, you can say, okay, it's better to associate, connect to this base station, but not the other, or you should switch. So there's also a load balancing problem. Okay, so in brief, a variable here could be power, could be base station user association, like a mapping or pairing. It could be also a kind of frequency allocation. Of course, if you consider time slot multiplexing, the resource could mean time. But here I will focus, just simply use the notation, say, okay, power is a variable. You would like to choose or adjust for the optimal performance. There's also a question, what would you like to achieve in terms of, let's say, the average throughput of the user, which is a function of signal to interference plus noise ratio, or would you like to give some fairness to the edge user, which is very far away from the base station? So you can define your utility, okay, which can be denoted as a function. So what we like to do is to have a kind of solution which can optimize this system to maximize, let's say, your utility function of the whole network among the base station, among the users, okay? For the downlink, you will say, okay, the utility is measured by the performance of the users. If you consider uplink, then just the opposite. You say, what is the uplink throughput? Okay, now I'm going to use the case of downlink in particular to clarify. You would like to develop some math tools or algorithm for doing so. You wish scalable and distribute, which means less information exchange between the base station is better. Or you will say, I don't need a central controller, or I don't need a central device or a computer to make the decision how I should decide the power for this user or that. Because when the network is large, the decision could be very difficult, and the information exchange could be very heavy, and the delay will be large. If you have to inform one from another in a large network, it will take a lot of time to inform one after another, and the decision will be too late. Of course, this is in the category in the literature, we say self-optimization, or if you trace back to the old literature, people will say this is the SON, self-organizing the network. So the principle here, or the objective, is that you would like to have a kind of a local operation, distributed algorithm. You measure something locally from the user, okay? Let's say locally, for making a decision, such as a local measurement of interference, signal to noise ratio, or similar. You say at the end, I can make a decision, okay, in a distributed manner, such that the throughput of the users in the network, if I define as a sum rate, it will be maximized. Or if I define as a proportional fairness, it will be maximized. You can define what you like: throughput, energy efficiency, fairness, or as a function. So here, I just give an example that the variable could be power, could be channel, time, frequency, or the client-user association pairing. Okay, like the figure on the right side. Of course, the problem is not about a single cell problem. It is a multi-cell problem. Okay, otherwise it would be easier. So I will just give you a few terminology to introduce the background. So I'm using this very typical or simple network, such as LTE for 4G or 4G plus. You say, okay, now I'm going to reuse all the resources, such as the frequency or power for all users, which we call reuse one system. I'm going to introduce this topic in terms of downlink, such that this is just a base station. Cell 1 transmit to user, the mobile phone. Cell 2 will transmit to the user, UV here similarly, okay? And you will see the red and the blue, the link. You have this signal or interference due to the network pairings, the users. Of course, you can do your power control such that your cell will be bigger or smaller, the coverage. What does it mean by resources block or frequency? Simply means that you have your frequency spectrum, you divide. Yeah.
Viết là không phải là C mà là KE đúng không?
Should I continue? Yeah. So your frequency band can be divided into multiple subcarrier, such as this in the y-axis. Of course, in this general system, you can also divide your time into multiple time slot. So here, in brief, in that vocabulary, just mean a user ABC can use each block, or can be assigned by a block frequency time slot in particular. Of course, once you assign it with a frequency time slot, there's a question in general at the same time, what is the transmitted power you wish? They say power equal to 1, power equal to 2 or power equal to 10. Okay, and then when you measure the signal to noise interference noise ratio, you would see that as a division, signal divided by the interference plus noise. And we can skip the right side diagram. Just this is the physical layer. We will not worry about that here. This is about the modulation scheme for reference as appendix. So we would like to design algorithm. Okay, this problem usually is non-convex, non-concave, and that's the challenge. If it's a convex or concave, it's more possible to solve it very efficiently using, let's say, convex programming standard method, or using the gradient to find your solution. Okay. Since it's non-convex or non-concave, we usually have a little bit problem. So of course you can consider to solve it by convex approximation or concave approximation first. This is a issue that when you approximate, maybe there's a sacrifice, okay, of your performance, and of course you will have a simple problem. Okay, so here I would like to address, say, okay, we are not going to simplify the problem. We are looking at a non-convex or non-concave problem. Even when you are allowed to centralize the algorithm, it's not easy. So in this category, usually people would say, okay, let's look at the non-convex function problem. Let's see if we can solve it by centralized algorithm. And then after that, let's see if we can implement the centralized algorithm or develop it in a certain manner such that they become dispute. Okay, so step one, you find a solution method to solve it nicely, no matter it's centralized or not. Step two, then you derive your centralized algorithm or extend it to a distributed version and hope it would have the same result. We know when it's a non-convex, you can do a searching method anyway, how to particular, let's say, a Hungarian method, but it has a high complexity. So the central question here is that can we have a way to solve this problem such that the figure here on the right side, okay, you say, okay, I have many user, let's say user is considered as a node in a graph. Is there a way to configure the node or the devices, let's say the power level, in an autonomous manner, which means more distributed or more self-organized or locally, such that you will have a very good, let's say, interference management result, such as maximizing the sum rate or maximizing the proportional fairness. And this is the question I would like to ask in this talk, or to comment a few. So here, this is a literature. We know this category, the NUM, the network utility problem. We can say if it's convex, we know how to do it in a gradient method. If it's non-convex, there's a centralized or dispute. When you would like to have a distributed algorithm, what does it mean is that we hope that this solution will work for any network structure, which means the graph in any manner you like, such as a typical mobile cellular networks, Orange network, or where we can see in Paris. You would like to consider solving maximizing for any utility function, arbitrary cost function you like. It would accept, let's say, the configuration, let's say power in terms of a discrete power level, or it also accepts the variable. It's a continuous variable, okay? And sometimes you work for this or discrete. Sometimes it works better for the continuous, just to introduce the variable at the state. You wish it can work in a asynchronized operation manner, which means you don't have to adjust the power level of each devices in a certain manner predefined, such as user 1, 2, 3, 4, user 1, 2, 3, 4 in a round robin manner. Maybe you don't have a way to coordinate them and ask them to follow one after another. Okay, you want to do it in a more arbitrary manner, which means random sequence. You wish to have a limited information exchange and also computing requirement, because some function when you would like to compute could take you a lot of effort, will mean a lot of time in your computation, then the delay will be large, and the parameter for this equation or system will be outdated. You can say this is the fractionness of the information is no longer available, and when you solve the problem, the solution becomes suboptimal because it's too late. And you wish it's not only heuristic, but you can prove it works with a convergence property and guarantee where you will go, the solution finally. I will just put it here just for reference, but we don't have to look into details. You can see this kind of a question has appeared in the literature for networking research people, like transactions or networking research. It go to communication information, Infocom, or many other. Okay. Of course, you can trace back to the earlier work, such as in the math or computer science, when people would like to solve it using, let's say, a potential game theoretical approach, or similar annealing or meta-heuristic. This is more in the math or part of math literature. And it is not surprising that the decision has been in the Markov chain Monte Carlo simulation literature. Okay, and there are a few books I put here for your reference. If you're interested, you can look and find a book in the even I link some of them. So as mentioned, this problem, first we can model it as a locally coupled network system. Okay, each node has a possibly non-concave local objective function. Okay, what does it mean by that? For a node here in the example means a smartphone or user devices in the downlink. The measure of the performance of these devices is in terms of SNR, in terms of, let's say, achievable channel capacity, the log 1 plus SNR. And then even sometimes you put a log function on that, or utility function of fairness on that, such that the measurement, the objective function here is not a polynomial, not a simple linear function. It's a non-concave objective function. You would like to control a parameter, right, or to adjust, let's say, power level, which from the base station 1 to its user. This is a local state. Depends on the local state of this node, and also the local state of other nodes, which means the power from the base station 2 to the user in blue here, which will impact these devices. So you see that the measurement, the performance of these devices of base station 1 is a function of this node, the local state of this node, and the local state of all the other neighboring nodes, as long as they influence this user, let's say signal propagation. You would like to maximize or minimize something, let's say called global utility, mean all the devices, all the nodes, how they will be satisfied, the throughput, the fairness, or even if we like to consider in the physical layer, such as bit error rate or coverage probability. Okay, so is it doable? So here we can consider, let's say, using a learning-based algorithm by using, let's say, this SAP, which in the literature we say spatial adaptive play in potential game or game theoretical approach. Okay, what does it mean by spatial adaptive play? Which means if you consider this as a node, we have 5 here as a graph on a map. Okay, it's a space. So you will do configuration of each devices on the map adaptively and just go around. Okay, this is what we mean by SAP, spatial adaptive play, again. So in this, there's a connection of this literature SAP to the MCMC, for example, give sampling. You are going to do iterative randomized configuration of the devices, okay, which means the power levels. Here, I will focus using the vocabulary power for that, but you can consider the state of the node is not necessarily power. It could be whether this user should go to the left or right, and there are 2 choices. Or should I go to channel 1 with base station 1, or channel 2 or 3? Because if they are going to use the same channel, I mean, for user 1 and 2, you can use different channel to avoid the interference. Okay, there's a called channel interference issue here too. You can use, let's say, best response according to the game theoretical approach, define a deterministic algorithm. By best response, which means that the decision of the power level for this user, okay, from the base station 1, you choose the best due to your local measurement, okay, the maximum, the greedy algorithm. If you use a maximum power for me, such that I will have a large throughput, do it, okay, best response. Of course, by doing so, it may not work for the other user. Okay, we have to be careful, or we have to be to see how we have to balance among the user. Okay, so best response is good in the sense it's clear, straightforward, deterministic, and it can, if there's a condition and property such that, for example, it can converge to, let's say, Nash beam, then it will converge very fast. Okay, but of course here there's a drawback. By doing best response, very often or sometimes it does not guarantee you will have a globally optimal network solution. Okay, because intuitively you are doing a selfish, greedy decision, and if everybody do that, it's also very possible that it will just become something chaotic, or you go to somewhere not globally optimal. Okay, not for the whole system. Okay, it's a kind of optimal solution, or you say local optimal point. So here, of course, for wireless system, you may take this assumption. Okay, the size of neighbors in the graph or among the user, I mentioned earlier, the node is relatively small compared to the entire system. Okay, otherwise, what does it mean by this? It means the wireless signal will propagate proportionally to the distance in between the devices and the user. Okay, I mean the base station. Since if the distance is large, the signal receiver at a point, a node, will be relatively small, and up to a certain distance, you can say this is relatively small and negligible. Okay, such that here I intend to suggest or assume that the graph, okay, I will show you a graph later on, that it is not fully connected. Okay, of course, if the graph is fully connected, it'll be more challenging. Okay, unfortunately, due to wireless, the wireless network is very dense and large sometimes. Okay, but fortunately, the signal will propagate and decay due to distance. So you can say, okay, fortunately, we have a not fully connected graph, and it will be easier to tackle by our distributed algorithm by divide and conquer in a certain manner. So you can model it as a potential game. Okay, I will show you some notation or math a little later, but I will keep this presentation in a more high-level discussion. Okay, and we do formulate define this problem in terms of the spatial adaptive play, and there's a reference here. Okay, so here to say that you have your base station, you have your UE. Okay, like these figures, you can accept macro cell, micro cell, any base station of different power levels. You can consider different utility function. Okay, such as what I show you on this page. Here, A, B, C, D are the nodes of a graph, which means devices A, devices B, such as the smartphone, or the user, the receiver. You have your base station to transmit. In the graph, you don't see the representation of the base station, because what you care now is simply what the devices the user will receive in terms of SNR or delay or throughput, for example. The node A, B, C, D, okay, has a state. Here, state could mean power level you transmit from the base station to the user. Let's denote by XA, XB, XC, XD. Of course, this could mean frequency if we are doing another resource allocation. Okay. You will say now you would like to divide your local objective function for A or associated for A. Okay, we use, for example, FA, FC, FD to represent this local objective function. Be aware that the local objective function is not necessarily the throughput or the measurement of for the user A. Okay, for example, you can say what I care is the SNR level or throughput of user A. Okay, that's it. Here, FA in this also depends on for purpose of the optimization algorithm design or numerical reason, you can define FA as a local objective function, not only considering the signal to noise, the throughput of A, but as a function of A and B at the same time. So you see by the expression or presentation F, okay, F is not simply a local selfish function, okay, who only concern the user A. If you define FA in this manner, okay, let's such that it is the throughput of A plus throughput of B in a certain way, okay, a function, a combination. You see, this is a social function, okay, taking into account the selfishness of A, but also you would like to care about B, what is the throughput of B, okay? Of course, you can ask the question, why not F of A containing the throughput of A as a function, B and C and D? Of course, you will see mathematically or in algorithm design, in this you intend to make it small, okay, because this will be better for, let's say, in terms of computation or information exchange requirement. On the other hand, you would like to make it in a certain manner such that it's sufficient or it's large enough that you will take into account what's happening around your neighbors or for the whole networks, A, B, C, D. Okay, you can imagine the extreme case that your FA is only a function representing or containing the throughput of A, but not B, but not C, but not D. Then simply this is a very selfish and greedy decision for yourself. Okay, and then in this at the end, you will just realize that this definition will not work for the global network optimization problem. Okay, because at the end it will become chaotic simply. So that is important to in this to define your local objective function in a certain manner. It will work for the whole network. So let's say you have a node A arbitrarily chosen like this graph. Okay, what you're going to do now in an algorithm or operation, you will select a local configuration of your A. Let's say the power level. Let's say in the beginning, your power level for A is XA. You may consider to change it from power equal to 1 to power equal to 5 or 10 or 12 or any number you like. Let's denote it by YA. Okay, so you would like to have a state transition from XA to XB, and given the XB, XC, XD, I mean, let's assume BCD have the same state at that moment, okay? And we denote this by a function, let's call it Q. And we can define by this exponential function. And you see that the F is the one I mentioned earlier called the local objective function. It could be a function of YA, I mean, of the state of A. It could be a function of A and B. It could be a function of ABC or a function of ABCD, depends on your choice, which this is the job of algorithm design. And of course, it will impact the proof of convergence and other in the future. Okay, I just put the letter ABCD here to say these are possible, and I don't mean it's a must to include ABCD in F. Okay, but I would say you should. It's also that if you only put A here, it will not work for the global optimization problem. Okay, and this is the trick or difficulty of the research part. So you divided this local objective function F associated with A to divide to a constant called T. Okay, I will clarify what's T. Okay, T is a strictly positive constant, which either you say normalization constant or scaling constant. You would like to use exponential function, okay, because it's a nice shape, okay, and in this it will work. And exponential function is also necessary when you prove the result, okay, and I can go into the details, okay, or the reference when you are interested in the future. So you can say, okay, I'm going to make a transition of my power level of node A from, let's say, XA to YA. There are many choices of YA. Let's say now you're using a power level equal to 1. You can go to power level 2 or 3 or 4 or 5 up to 10, or even you can decrease, okay, to 0. So among all of them, okay, let's say you have a power chosen power value from 1 to 10, you can choose. You substitute your power value into this function, okay? And you see you have 10 numbers by substitutions. And this become a distribution. In this, when you normalize it, you become a number between 0 and 1 in probability, okay? And we are going to denote it as probability. So you do a transition from XA to YA for the node A. And if you just go to a state, let's say power 1 or 2 or 10, okay, which give you the maximum local objective value, the FA, this is the best response decision. In this, there's another way to do it, which you do not choose the best, but you choose one according to a probability distribution, okay? And I will give you the detail, which means you don't simply choose the best because you would like to keep some exploration such that you may choose the second best or the third best by a certain probability, such that you explore the space a little bit, and you hopefully at the end you will find the best solution for the whole network, but not simply the greedy one, which usually would go converge to the local maximum solution or global optimal solution. In the context of simulated annealing or MCMC, T is not simply a fixed constant in terms of in your algorithm, okay? But you will choose your T adaptively in a certain manner in a process we call annealing process, which means T will start from a positive constant, let's say, for example, 20 or 1,000, any large number. You decrease it step by step to a lower number, let's say decreasing from 10,000 in the beginning, initialization of T, finally gradually becomes 0, or let's say it's very small, close to 0, okay? So this is the process, and in this T means in this literature called temperature in the annealing process. There's a question in the literature too, how you're going to decrease this temperature T. Should it be linearly decreasing? Should it be a log scale decreasing function? Or should it be exponentially decreasing function? Or could it be a polynomial? And what's the necessary condition or sufficient condition for that? Of course, there are two, there's a trade-off. If you want to have some property to guarantee this simulated annealing will work and give you some strong guarantee of the performance, you cannot decrease your T too fast or just jump from the maximum temperature, the constant, to the minimum. And on the other hand, when you decrease it too slowly, I mean, you realize that you need too many steps to decrease, okay, which means too slow. So you would like to trade off among the two. And this is another research problem in the literature, okay? And from the reference, there are many decisions about that. Should we do the cooling or not? Should we do annealing or not? And how fast or how slow it should be, and how to do this annealing, okay? So the graph here, as mentioned earlier, in this you can interpret it as a Markov chain. You can interpret the local update, which means how you're going to change your power level for A, B, C, D as transitions in a reversible Markov chain. And this the way that at the end you can prove that the convergence property. Okay. So when you do this kind of a transition, let's say per node for A and B and C, you don't have to synchronize your transition. Okay, which means you can choose A, B, C arbitrary, just draw a coin by equal probability. You say, okay, this time I choose B, let us configure it and do a transition. Next time you choose again, maybe you repeat as B, or maybe you go to C, or maybe A or D. You choose one node randomly. You do the transition according to this exponential function. Either you do it like best response, means go to the one, give you the maximum local objective function, or you choose it in a certain way using a probabilistic manner. Okay, I would give you the expression how we write that precisely, what does it mean by choosing it in a probabilistic manner. Okay, in that probabilistic manner, in the literature of MCMC, you can say this exponential function divided by t, we define a Gibbs field. Okay, and F is a kind of a local energy. So as I mentioned earlier, F, this is the local objective function, but you can say, okay, F here in this vocabulary of statistical mechanics is just kind of energy. You wish the energy to be as large as possible or as small as possible for some reasons. Okay, so when the T goes to 0, if you do annealing, okay, let's tune it, but not simply using best response. You will see that indeed it's possible that the whole network, such as the graph ABCD, will give you best configuration, which means the sum of the local objective function of A, B, C, D. Let's say, let's define the global objective function as the sum of the four. Okay, could be maximized or minimized. Okay, it depends on your definition at the beginning of the problem formulation. If you do not do this kind of annealing or change the temperatures step by step in different in your algorithm, you say, okay, T just a constant, let's say become 1, okay, since the beginning, and let's run the algorithm, many iteration. It will go to a certain state, and there's a guarantee where it will go, but you will not guarantee it will go to the best for the whole network of ABCD, okay, because you just go to a function which is a local point. Since this is non-convex or non-concave, you can see that there are local maximum point, global maximum point. Okay, by doing best response, it just means that you will go to somewhere, the local, not necessarily the global. Okay, of course, by luck, you will go to the global by chance. So how we're going to work it out? This is a graph. Okay. Here, if you use the potential gamma spatial adaptive play framework, you consider this non-concave function that you would like to maximize. You can use gradient method, which you will see you will get trapped in local maximum point. You update your configuration for A, okay, just like what we mentioned earlier. You can choose A, B, C, D arbitrarily in each configuration step iteration. In this is a distributed one, right? Implementation, because now you don't ask coordination to decide which one should go first. You just do randomly, okay, spontaneously. Secondly, when you make the decision for A, you say, I decide what is the power level for A such that my FA is, let's say, maximized if due to best response, or it go to the good one according to probabilistic distribution, which means export version. Okay, in this they are just working in the same manner. Okay, but just in the algorithm, you will say go there for sure or not for sure. Okay, just a code. What I mean by FA and why is a dispute or local operation, because if FA is a function in terms of A and B, you see, you just need to know, let's say, for example, the achievable rate of A and achievable rate of B for that configuration. Okay, you don't ask the question, what is the C and D? And this will require global information change for computing all the equations or measuring the throughput. Okay, of course, you say we are a little bit ambiguous here, right? We do considering the neighbors, okay, but not all. So I have to say maybe it's more regular to say this is a decentralized algorithm. It's not really fully distributed. You still need to measure something from your neighbors, okay? In a certain formulation for a particular problem, in the one I mentioned earlier in the beginning for the wireless LTE, we do have a literature. We define the FA, okay, in a manner that it FA take into account A and B, and that's it. Okay, and here we see that you need account of a two-tier neighborhood information exchange, and as example. And don't be surprised. Sometimes you may need 3 tiers or maybe 1 tier, depends on your utility function, depends on the network interference graph structure, and this or that. When you really have to solve the problem, you just have to look at the graph and use the same vocabulary or tool, and you will see what's the minimum you have to do. Okay, it's quite natural. You cannot decide whether you should only involve 2 or 3, because if the graph is connected in that way, or the local measurement must be taken into account all those neighbors such that you can prove the convergency, then you have to define that way if you wish to have a strong math guarantee, okay, for your algorithm. That's it. Okay, here I hope that this notion of FAB in this graph is clear to you. So now what you're going to do, the global state of this graph or network is denoted by S. S is a allocation of the state of all the local node. Okay, as you can see, the global objective function is a measure of the sum of all the local objective function. You are to maximize your global objective function subject to S. Okay, the global state. Your algorithm is simply just in the equation here. You write your exponential function as mentioned earlier, using your objective function f divided by a constant we call temperature, okay, or by annealing, you change it gradually. You divide it by this number, which means sum of what you can configure, okay, for your node among all the states possible. Okay, let's say power 1, power 2, power 10. You don't know which one you should do, but you know all the possible choice you can make from relation to this particular user. And you can see that this is simply a constant, okay? Not because, not due to the one you would like to transit, okay? It just gives you a constant. You can say now this is simply a normalization constant. You can treat that constant C. And the pi on the left-hand side in this is a vector, okay, of this function. If x equal to 1, you have a 1 for pi. X equal to 2, you have another. So you see, if you have a 5 power level, you have a 5 choice, and each associated with a number pi. In this, when you do this normalization, this pi is in the interval of 0 to 1. And this is the sum of pi equal to 1 by this normalization. Okay, so in this is a probability. In this, it can be interpreted as a probability, and we are going to use it as a probability later on for the decision making. If you use the explorative version of the SAP for your algorithm. So let me start from the case we use the deterministic version. This is a finite potential game you can prove. Okay, when the players update per the best response, that's called BR, in a round robin manner, which means synchronized, or random, or synchronized, okay, mean arbitrary. At each time a player update the power level or the strategy with the best response, all the player will do this spontaneously, okay? And here, as you may see earlier, when we use the FA or FB, the local objective function, this is a social performance measurement, okay? So it can be proved that at the end, when you do this game with best response, it will converge to natural equilibrium for sure, okay? You can also use another technique using an explorative learning algorithm, not necessarily go to the best, okay? But you are going to use this distribution, which means for power level 1, 2, 3, 4, 5, up to 10, you have a different probability, the pi value. Now you, according to this probability distribution, okay, you go to the one with a higher probability or less, depends on what this distribution means. Okay, not necessarily go to the one give the maximum. So this is the difference between the best response and the one on the bottom. Okay, which means explorative learning. By doing here, in this, you will see that the best response only guaranteed to go to natural equilibrium, which could be a local maximum. The second one, the explorative one, will guarantee you as time going to infinity, which means you do many iterations for this problem, then you will converge to a strictly global optimal solution with probability 1. Okay, this is what we can claim. Okay, of course, you will see that in this algorithm, there's a local utility function, local objective function V. Sorry, I didn't use F here. You have the exponential function E. You make a state transition. Okay, you would like to go to the next one you wish, from T to T plus 1. There's a beta you can control. Okay, if you make beta equal to 0, you will see just by mathematical substitution here. Okay, you will choose each power value level with equal probability, because at the end the pi will be equal, have the same number for any state by pi equal to 0. For large pi, okay, let's say 10,000 or infinity, okay, then you see that in this, you will see the probability mass will go to the one which are most favorable to your local utility. So you see with probability 1, you will go to the best response result. Okay, and in this, it's not necessary you choose 0 or beta. Okay, you can choose a number in between. In this, in the vocabulary earlier, we used the notion T, capital T, and T is 1 inverse, 1 divided by beta. Okay, so you see, you can choose a beta or the temperature T in between the two extremal case, by fixing the value. Another version is that you choose beta as a time function in kind of a cooling or annealing. Okay, there are two different strategies how to do it. And this is the connection between the two literature from the potential game theory literature and the MCMC, the statistical mechanics meta-heuristic algorithm. Okay, and both will indeed have a similar result in that manner. Okay, and one is more from mechanics, physics, and the other is more from game theoretical approach. Okay, so what we can guarantee or say here, yes?
I have a question here.
Yeah.
Isn't for what you showed before on this slide, beta can be considered as the inverse of the temperature or not?
Yes, the beta can be written as 1 divided by T. And sorry, I confused you because I use two different letters for the same meaning due to two different literature. Yeah.
So is it equivalent?
Beta equal to 1 divided by T.
Okay.
Yeah, they have a different, yeah. Beta is more used by people in the game theory, and T is more used by people in physics. Okay, and since I copy, I didn't have a chance to modify the letter. Okay, but you can consider it just a parameter to tune the system, like cooling system. Okay, so when you look at this expression, you interpret, and you can see different choice of beta will give you some different phenomenon. Okay, smaller beta or large beta, or smaller temperature T or large temperature T. Okay, beta and T are a matter of configuration or control parameter for the system. What we mean by the cooling scheme or the tuning annealing is that you would like to suggest a beta function if it's a function in terms of time, such as log, okay, 1 plus t. When time go to infinity, of course, this will go to infinity too, but you see it's a log function, okay? And if when t is 1 divided by beta, you will see when t go to infinity, 1 divided by t will go to 0. So you see in the other literature in physics, the temperature wish to go to 0. Okay, you wish to make your temperature go to 0 when you do annealing. Okay, so it's just opposite. But anyway, for algorithm or computer science people, like implementation here, it is the same. Okay, either you write beta or you write v divided by t. Okay, multiply or divide by. So you can start from any arbitrary state of the network. Let's say you recall the memory, you have the node A, B, C, D. They are in initial power levels. What is nice here is that you don't mind where the network starts from. Okay, if you run the algorithm like this, you will always go to what it is expected to. Okay, so some algorithm does not work in that way. If you start from a bad initial point or configuration, you will never achieve what you like. And here you don't have this issue. So I'm going to use, I will go, sorry, a little bit faster because of time. I don't want to bother, spoil your lunch time. So what I mean by SNR is simply like this graph. Okay, you can see in the top, you have power multiply your path loss, denoted by L, and forget what's I and BC, which could be denote the user I, denote the base station I, denote the carrier, the channel I. Okay, let's forget it. The first term here just mean the power for other user J, path loss due to that, and alpha is just a parameter like spreading code or something like that. You can forget alpha, okay, for wireless system. So the first term is the interference power from all the other user, and W, you can say this is noise. Okay, that's it. You have your SNR for your user I, the smartphone I. You put it into your function that you like, such as utility. You say, I care about the throughput, I care about the delay, and U is going to represent that. The sum of your all your user is denoted by capital U, and this is your global utility function. Okay, that's it. And you see that, for example, if the parameter is to adjust to optimize the power P, then that is your state, okay, which you are to tune and to do transition. To say that it's not necessarily that you are interested in the throughput, but you can also say I'm interested in the proportional fairness. Then you will use this log function to impose this criteria. Where you say I would like to minimize the delay, then you will do 1 divided by the throughput, and this means the delay somehow, okay, and you would like to minimize, okay, you can do in the way you like to define your utility function. What we can say, and I will just comment here, okay, if you are doing that, you define your user or the smartphone as a player in this graph or in this structure. You say I'm going to apply this strategy, okay, using the state transition. Okay, and here, sorry for this copy and paste. If it's a user associated problem, then your state could mean base station selection, C means the frequency carrier selection, P means the power selection. You multiply all the possible combination of choice, and you define your local objective function. And here in this vocabulary, we mean a payoff function, which is sum of the measurement of throughput of user 1 or 2 or the neighbors, okay, like A and B in the previous example, okay, and V is what we mean by capital F in the previous slides. So this is simply a typical strategy form of the game. That's it, okay. I think this is quite typical in any textbook. You just plug and play this notation to, and now you can check whether this would be a FIP, okay, the finite game, and we are able to prove this and show that if you can define your V in a certain manner, okay, due to your U and by the neighborhood, okay, this is a social function which fulfill the property in some cases, it depends on your problem, and it admit the FIP, then you can prove it converge. Okay, and that will be nice at the end. And of course, it's not free lunch. You cannot simply say, I pack anything I like to this play off, and it will always work. No, you have to check carefully. Okay, how you define your neighbors, and at the end, it guarantee and allow you to prove this, satisfy this condition. Okay, in the finite game. So at the end, when you see that you are guaranteed to converge, then what you're going to do is simply do your best response, like the first box on the top, okay? Or you choose the other one, say you do annealing algorithm, okay, like the Gibbs sampling, okay? Like this one, choose, give some probability to go to the second best result, not necessarily one, okay? And sorry, this is the one I should put earlier to answer Ludovic, the beta and T. Okay, the beta is due to this potential game, T is due to annealing, the different literatures. Okay, from two different books when I found by chance. So we do simulation, okay, and we use the typical path loss model for 3GPP, like distance, noise, etc., and we simulate by computers. And I'm going to show you that the two simulation results. First, we would like to maximize the sum rate of the user, which I call SRM, sum rate maximization problem. The second, we say, okay, now we wish to see if we define the utility function as a proportional fairness, which means log of your throughput. Okay, and initially, this is the problem to solve. The red triangles mean the base stations. The blue dot means the smartphone. The link, the pink means the association. So this is what happened in your network, let's say in Paris, okay? Just arbitrary. In this, you would like to see what happened. Of course, this is not optimal. You will see this is what happened at the end if you consider proportional fairness utility. So you see, first, the user to base station association is more evenly spaced, more not overload. Okay, and of course, this is another case if you do summary maximization. Okay, when we investigate this configuration, realize this somehow this just means you are going to sacrifice all the other user. This is very bad which means they're far away. So if you just want to maximize your sum rate, you let this poor user go away. Okay, zero throughput, and you invest most of power to the user which are very close to the base station. And you maximize the sum rate. Okay, and this is fairness. So you see, it did not maximize the throughput, but it make everybody happy in a certain way. Okay, and I'm going to show you just two figures, and then I think I will stop. Sorry for the time. So the first group of the one on the top is the result if I'm maximizing the sum rate of the system. Okay, the second result by another simulation setting, okay, is that I would like to maximizing the proportional fairness. The y-axis is the sum rate of the system. So you see that when we try to maximizing the sum rate of the networks, you see the algorithm they give you the improvement by time iteration. Of course, the sum rate of the user in the case when you're maximizing the full proportional fairness will not be high because this is not objective. Okay, just I put it in parallel as a control experiment. Okay, what's interesting is that the best response in purple, okay, give you a nice performance, but it gets stuck here because in this we know it will only go to the local optimal sometimes. The one when you do annealing or MCMC, you will see it may not go to the purple in the beginning because it will just do some poor decision or second best decision. But sometimes finally, and it will go to a better and better if you allow more time. Okay, of course, it is a cost that you have a larger number of iteration allowed. Okay. Now I'm going to show you in the plot that if you plot again in terms of utility function of proportional fairness. So this is the one that from the result of proportional fairness when you apply the utility of PF. Okay, So you see that in this, we are able to maximize the PF as much as possible. The blue means the best response, as usual. The red means something you explore and getting better and better. Okay, of course, don't be surprised these two are very close. There's small minor difference. But in this, when we do proportional fairness, the gap sometimes is not very large, but they do have a small difference. Okay, as you can see. Don't get surprised of this summary maximization problem result because it doesn't maximizing the fairness. Of course, you just get very poor performance as a control experiment. Okay. I will skip this slide. This is another simulation result to say in this, sometimes you will need a lot of iterations. Okay, if you do, let's say, similar annealing, and this is not surprising. So there's a central question. This is a literature studies that how you should cooling your system and to guarantee good performance at the same time to be as fast as possible. And this is something it's hard to. And people are trying to develop faster and faster algorithm for that. Okay, and I will skip this slide of a similar result. You can see this kind of phenomenon. Similarly, you need more time to converge, and it will up and down because you are doing a kind of exploration from time to time. Okay, and I would just skip this appendix, which is a kind of another application, which is not in terms of power, but in terms of the eICIC ABS, the supply resource allocation reservation scheme. Okay, and just another story. Okay, examples. Okay, for another applications. Now I will go to a conclusion slide to say here we have a category or family of algorithm which allow you to do a kind of a decentralized optimization of a network, which could be wireless. In this, people do apply this to wireline network too. Okay, you can show you the slide, the reference paper. You can formulate this problem as a potential game and SAP. You can also apply this using the meta-heuristic MCMC method using explorative learning, or precisely using, let's say, gift sampling method. Of course, here in all this setting, I just say we are going to solve this problem by tuning the parameter power control using all the given parameter, like the linking and this or that. Doesn't mean we are so everything is given. Of course, this is still very ideal, okay, or simple assumption. You can't expect your linking measurement is given precisely, static and known without delay. Okay, for example. And what is interesting in the literature is that how you're going to have your faster or fast cooling scheme. And this is an open question for some literature. Okay. I think that's all. I will stop my presentation here and to say that this is applied to mobile network resource allocation problems. You can do joint optimization of power base station pairing, user base station pairing, channel allocation problem. You can connect this technique to potential game or game theoretical approach. You can also connect this to MCMC method or the metropolis algorithm, or in the large category, which people call interacting particle systems. Okay, and this is to allow you to have a kind of spontaneous or locally operation such that to maximize the complexity function. And I will stop myself here. Sorry for being overrun of my presentation.
Thank you very much.
Thank you, Karim. Thank you.
So maybe we have time for a couple of questions if there are in the room.
Yeah. Yes, thank you for this. So my question is how these things are, I mean, were these things used in practice, I mean, by Nokia or Alcatel in the past into things which are implemented in practice? That's
yeah, Francois. In this, we used this for 3G in the beginning. At that time, when you and me, we are working for Alcatel-Lucent. And the more recent one is that we extend this result to this. If you can see my slide, the eICIC, or in this more recent, we call the FeICIC, the further enhance the intercell interference cancellation, intercell interference match problem. So which apply to the 4G plus or 5G, that you would like to adjust or control your cell selection bias. What does it mean by that? It means that you have the macro cell and small cell, and sometimes your macro cell, the big cell, simply overload. And in 3GPP, they wish, of course, this is not very nice to do it that way. They say we have to impose a particular number offset to each base station, such that by using this artificially, you are going to kick off the user in a certain manner. The question here now is that what is this number for each base station, such that you will kick out the user from your neighborhood, okay? And in this, I solve that problem. And jointly, there's a question that what is your duty cycle factor for each base station? In this, it just means the time slot and frequency slot reservation for each base station, which means you are not going to use reuse one system now. We did use reuse one for 3G, but later on in the 3GPP, they said no. Because of course that would not be optimal. We know reuse one is theoretically more optimal, but in the 3GPP standard, is a technology. So they say no, we don't use a reuse one now. The question now is that for each base station, we use partial resources, and how are we going to decide this percentage? Let's say 10% of the time slot, 20% of 50%. And here, I find a chance to use the framework we developed in the old time together. That here the state are 2, 1. What is the offset, the O1, O2 for your base station? Second, what is your percentage, the alpha 1, alpha 2, alpha 3 for your base station? So to me, it's just a reuse of the technique. For each base station, you would like to make this choice. It's a discrete state in terms of alpha and beta, and you don't know which one you should go. So I say, okay, now by this combination, maybe you have a 2 times 3, you have a 6 state to go, and you put this in your local utility function using your neighborhood, and then we try to find the optimal alpha and offset for each base station, and at the end they accept this result, and we are happy to put this into their simulator and also the software somehow. And we did a pattern of this idea, not because of theory, but just an application at the end. And that was more for the LET advance. If I answer your question first of all, I can.
Okay, so what you mean is that in this case, there is 2 products, right?
They put into their model. They say the Enoch B, it was about 5 years ago, yeah, and in the product. But I'm skeptical. I don't know where is the product, whether it's in Orange or somewhere. But they took this idea in the simulator, the module. They say software model. Yeah. And at the end, this is how they implement. Yeah, okay, I forgot to mention. Yeah, they put into LT scheduler and together. Yeah.
So if there are another question, I have another one. So did anybody look into things when the size of the system gets very large? Because I mean, there ought to be interesting phase transitions, right? For instance, I mean, if you take the Gibbs sampler just on the eICIC model or things of this type, I mean, there is a famous phase transition depending on the temperature or things like that. So there ought to be similar things when you let the size of the system tend to infinity, whether there is some sort of percolation and and the convergence may lead to different states or things like that. Was this studied at all? I mean, the behavior of this algorithm when the size of the system tends to infinity.
Yeah. So when the size of the network go large or become infinity, it is not a big difficulty to the implementation people or the product people. because they would take their assumption that the signal will not propagate. I mean, the interference can be considered negligible when the distance is large. So you can say they are taking our results account of approximation, okay, or heuristic at the end, okay. So that network problem size is not an issue to them, because they will say, okay, I just consider the interference will not go that far away in my imputation. But what bothered them at the end by using this method is the path loss measurement or the linking measurement for calculation for writing the equation is not very practical, which means during the case of fast fading or when the system is very dynamic, they start to concern about the overhead of the measurement, the delay of the measurement, and how fast you can do that kind of a measurement. And for more static systems such as LTE, or let's say more static like the environment, it won't be a problem. But if the system becomes very dynamic, then it's a typical question now. Yeah, how you get your linking information CSI fast. Yeah. And of course, the algorithm cannot do much, at least at this moment here. Yeah.
Thank you.
So thank you very much. Are there questions on Zoom? Okay, so thanks again for having presented today, and I will see you in 3 weeks with the reading group.
Thank you.
Thank you,
much.
everybody.
Thanks.
Bye.
Bye.